to be able to describe the Bohr model of the atom. The puzzle of the hydrogen atom spectrum was solved in 1913 by the Danish physicist Niels Bohr. He proposed a model of the hydrogen atom that linked the atom's electron with photoemission. According to the model, the electron can circle the nucleus only in allowed paths or orbits. When the electron is in one of these orbits, the atom has a definite or fixed energy. The electron, and therefore the hydrogen atom, is in its lowest energy state when it is in the orbit closest to the nucleus. This orbit is separated from the nucleus by a large empty space where the electron cannot exist. The energy of the electron is higher when it is in the orbits that are successively farther from the nucleus. The electron orbits, or atomic energy levels, in Bohr's model can be compared to the rungs of a ladder. When you are standing on a ladder, your feet are on one rung or another. The amount of potential energy that you possess corresponds to standing on the first rung, the second rung, and so forth. Your energy cannot correspond to standing between the two rungs because you cannot stand in mid-air. In the same way, an electron can be in one orbit or another, but not in between. So, how does Bohr's model of the hydrogen atom explain the observed spectral lines? While in an orbit, the electron can neither gain nor lose energy. It can, however, move to a higher energy orbit by gaining an amount of energy equal to the difference in energy between the highest energy orbit and the initial lower energy orbit. When a hydrogen atom is in an excited state, its electron is in a higher energy orbit. When the atom falls back from its excited state, the electron drops down to a lower energy orbit. In this process, a photon is emitted that has an energy equal to the energy difference between the initial higher energy orbit and the final lower energy orbit. Absorption and emission of radiation according to the Bohr model of the hydrogen atom are illustrated in figure 4-8, which would be this figure on page 96 of your textbook. The energy of each emitted photon corresponds to a particular frequency of emitted radiation, which is equal to E of the photon is equal to h nu. So based on the wavelengths of hydrogen's line emission spectrum, Bohr calculated the energies that an electron would have in the allowed energy levels of the hydrogen atom. He then used these values to show mathematically how the various spectral lines of hydrogen were produced. The Lyman spectral series, for example, was shown to be the result of electrons dropping from various high energy levels to the ground state energy level. Bohr's calculated values agreed with the experimentally observed values for the lines in each series. The origins of several of the series of lines in hydrogen's line emission spectrum are shown here in figure 4-9, which is also on page 97 of your textbook. The success of Bohr's model of the hydrogen atom in explaining observed spectral lines led many scientists to conclude that a similar model could be applied to all atoms, though the Bohr model only works with the hydrogen atom. And it was soon recognized, however, that Bohr's approach does not explain the spectra of atoms with more than one electron, nor did Bohr's theory fully explain the chemical behavior of atoms. So at this point, I'm wanting you to be able to describe the Bohr model of the hydrogen atom.